Start. Awesome. Cool. Well, Yan, thanks for joining us. I think we're gonna have a couple people join a few minutes late, but that's okay. It's fun to have you. Yan and I have suffered through running the Harvard stairs together a few times, and I've managed to avoid defecating on the Harvard stairs. So I'm quite proud of that. And have been buddies for a long time. And today he's going to talk to us about some cool semi-open source robotics. So I'm just handing the stage over to you, Yan, but it's all yours.
Yeah, awesome. Hi, everyone. My name is Jan. As my job, I'm a product manager of what we call low-cost automation at a company called IGES. They're a German company, but they're located in Rhode Island. And the whole department is branded low-cost automation. And what's really interesting is that the goal really is to figure out how to broaden the use cases for industrial automation. That includes robots, but also all kinds of other, automation that you might not think about when you think about robotics. But there's many bottlenecks right now that kind of hold up the adoption of automation in factories. We see with the big car manufacturing plants, a lot of automation there. If you think of a car factory, it's fully automated, and it looks really, really cool with a bunch of robot arms and everything else. But if you look at other segments of the industry, like consumer goods or retail, logistics, there's still a lot done by hand, which comes with a lot of different pain points. So that's what we're here to solve. We're here to kind of like understand what are the problems in the market, why aren't robots adopted in smaller companies, and how can we do something about it? So it's a really fun job. We're having a good time. Anything from looking at it from a markets perspective, but also looking at building components and building systems that are, as Max already kind of explained, semi-open source, and that's something that's really important. So I'm going to split this a little bit. I'm going to kind of like go through my normal presentation, kind of like share the problems or what we're trying to do. And then we can dive a little bit deeper into like the actual robot arms that we make and how to program them and everything. And then hopefully we have a lot of time after to discuss or chat about what I talked about. I'd love some feedback as well. So without further ado, I'll go and share my screen, and then let me see. Actually, let me.
This is the perpetual problem of can a room full of PhD and PhD students figure out how to share a screen.
That's good.
Is that what I just joined?
Yeah.
There you go. You should be able to see it. Thank God I only have a bachelor, so maybe I can push it onto that fact.
Yeah, we learned screen sharing at the PhD level only.
Yeah. So very aggressive branding, low-cost automation. Some people might think that's cheap. The idea is to lower the cost, lower the barrier of entry into automation, and specifically industrial automation. So let's see. Perfect. So this is a study from McKinsey from 2022. Kind of like saying that, and the most important sentence is on the top. The major bottlenecks for the adoption of industrial automation is cost and the lack of knowledge. So not really understanding robotics and automation, and also robotics and automation being too complex. And then on the other hand, way too expensive. So you can see that here it's kind of broken down into different industries, and you can see that the percentages are pretty high when it comes to cost. So it doesn't really make sense to automate something because the cost savings that come from automations aren't high enough for the investment to pay off. Another thing is that sometimes we just don't have the technology yet that would allow us to automate a task. Wiring cables, for example, is something that is really, really hard to do with a robot. It's very finicky, something that humans do almost everywhere. Haven't really seen really good solutions out there. And then also the third one, knowledge to how to implement systems. It's really, really hard for somebody that runs a factory to also be a robotics engineer, a mechanical engineer, and then an electrical engineer at the same time, while having to worry about the whole business on the other end. So we've seen the adoption of automation, in-house automation teams, like knowledge groups that can kind of work on it. But obviously that's a luxury out there. So what we have done is at IGUS, we've come up with low-cost automation. So basically what we're trying to do is we're trying to lower the cost of our robots while also making them easier to integrate. So taking the cost away. So I have a video here. It's kind of a case study, and sorry, it's in German, but basically it showcases the traditional approach versus our low-cost automation approach. And the application is a typical conveyor picking application. So goods come down a conveyor belt and then get picked and placed in a box to then be shipped somewhere else. So you can see on the left, we see a delta, pretty high pick rate. So you need a fast robot. And then you have a camera system locating the robot on the components on the conveyor belt. You can see some of the pricing here, but basically a huge chunk of the pricing is integration. And you end up with a total cost of 100,000 euros/dollars. Now, comparing this to the low-cost automation approach, you can see that, you know, the robot itself is a lot more affordable, but also you don't have a camera system or any integration tasks. So what you can see here is that it's super easy to integrate. So most people can actually do it themselves. And you have a 10x cost reduction. So an order of magnitude less. Another thing that's super interesting is that we use 2 systems instead of 1, but we're still being an order of magnitude lower. And I'll go into why that is and how we think about that. But yeah, that's one of the most interesting case studies that we've done, is that there has to be, for the people that design automation, there has to be, you know, different way of thinking about it. You can't just use the fanciest robot arm and then expect it to do something, but really have to, you know, go about something else. So we define low-cost automation basically with the goal that we want to automate stuff that we weren't really able to automate before, through the way that we approach it, but also through the robots that we use, and thereby lower the cost of the barrier of entry into industrial automation. So when you talk about this, or when you think about this principle of how do I make it more accessible? For one, the hardware has to be more affordable. So you really have to figure out, like, hey, how can I drive the component price down of those robots? Do I use robots that are less capable because they still fit into that application? Or do I, you know, build new robots? That's something that, for example, we as IGUS did. We built a plastic robot, a robot arm that you can see that is fully made out of performance plastics, except for the motors and the controls, obviously. But most of this is injection molded. The gears are 3D printed, and it drives the cost down significantly and makes all kinds of new applications possible because of the price point. And then second is the integration. So it doesn't really help you to get a bunch of robots in your facility if you don't know how to program them, maintain them, or make them work together. There's a lot of time, knowledge, and just experience required to really build an automated system for a factory. This is due to the fact that it's kind of complicated to program this. You do need to have people that know how to program and, you know, have some experience with what they call PLC programming. It turns out a PLC programmer at the moment goes for $70 an hour, which they do not have a university degree. It's just a trade. I think it's probably the best trade, or one of the best trades that you could do with a payoff. But in the end of the day, it's a very rare, these people, and that's why they're so expensive. And yeah, so there's all kinds of programs. And so if you want to make automation more accessible, you have to drive down the cost of the components, and you have to make it easier to integrate. so that you don't spend 2 weeks programming your robot to make it work, but maybe half a day to a day. That should be the goal. Because time is money, and if you have to pay a programmer 2 weeks, I think you all know how much that might cost. So cool. So what is the approach of, I said there has to be multiple things. You have to drive down the cost of hardware, and you have to make it easy to use. But there also has to be a systems level approach, right? If you look at an application, you can't just be like, well, I know that this robot arm is really good, so maybe I'll use that. We call the approach slicing the elephant. So basically, you've seen the Delta robot that was picking components from the conveyor belt. We're trying to break that process down into individual steps. So on the low-cost automation approach, you've seen that there was a guiding system that kind of like automatically placed the components in one spot. So you didn't really need a camera system anymore that located this. Then you had a pusher that would always push 4 of these components to the side to then have more accumulation. And then you have another robot that picks them and places them in the box. So one big advantage is that with only having to pick every 4th time, you don't need a robot that's as fast, right? So by slicing the application down into individual steps, you might have to use more robots, but the specs for those robots drastically come down. So you're just using a linear rail that drives back and forth, controlled by a stepper motor with a stepper motor driver, and nothing fancy about that, comparing it to like a Delta robot that has to pick 150 times a minute. So it's kind of the idea. And that's the approach that the people that are designing the system have to get to. Now, we can go into why that's not the case at the moment in the industry. The incentives are just not the right ones, but yeah. I think next, so basically, we need affordable technology. That means by slicing the elephant, you have to really figure out like what really is the precision that's required of your robot, how fast does it really have to go, and what's the payload. So there's the trade-off, right? If you want to maybe pick 4 items at a time, if they're all light, you rather pick all 4 at a time and move them, because that allows you to drive down the speed. If they're really, really heavy and you want to pick them at the same time, it might be more expensive to have a really bulky robot instead of using one that is a little bit faster. So those are the trade-offs that you have to do between precision, speed, and payload. So you can just see some of the systems that are deployed in the industry, but also that we offer and we develop ourselves. You can see linear systems, gantry robots on the left, 2-axis and 3-axis. Then after that, you see a Delta robot. They're also sometimes called a spider robot, and then a robot arm. So just to quickly maybe explain a little bit when you would use something like this, the gantry systems on the left, as you can already see, their workspace is kind of very efficient. So the ratio between workspace and robot size is really, really efficient. You have a lot of workspace, a lot of flexibility, and you can custom make them to your application. That means if you need one thing that is a little bit slimmer, you can just cut down the extrusion that this is mounted to, cut down the belt, and adjust it like that. Then you have the Delta robot that is really fast. So the workspace is quite small. That is one of the downsides, but it is really fast, as you can see. So if you have to pick from a conveyor belt really, really quick, Delta is your go-to. And then you have the robot arm over there, and you can see it can do all kinds of fancy motion profiles, kinematics, that allows you to do tasks that are a little bit more complicated. Typically, one of the most common applications is the pick and place. So picking something up and placing it down, that you can achieve with all 3 robots on the left. But then the second most common application is pick, place, or pick, flip, and place. So picking something up, flipping it out, down, and then placing it down again. And that's something that then a 6-axis robot, like those robots arm, come in really, really handy. Cool. Now, that's a lot of theory. We always like to apply it a little bit as well. So this is an example out of our factory where we have these injection molding machines. Basically, it's a press, and then they pump in plastic to mold it into a specific form, and then they release it, and then the parts fall out, just like an automated process. And you can see those metal kind of sliders there that are basically have to be placed inside of this injection molding machine to mold plastic around it. That was quoted to us by an integrator for, I think, around 70,000 euros for a robot that is barely faster than a human being. I think the human was able to load 4 of these in to the machine in about 45 seconds on average. So every cycle took 45 seconds. And now with this system, we got it down to 16 seconds. And yeah, I'll just play the video to show you how it works. But basically, you can see that instead of one robot arm, which we were quoted, that picks these with the camera system and vision and everything super complicated, we have a lot of small systems that work neatly together and then also improve the cycle time. So here you can see kind of a shaker table. They move it around and make these, include some randomization in them. And then there's a camera that kind of locates the one that can be picked. You have a suction cup gripper that kind of picks these and places them into a form where there's 4 of them. There's also a camera system that understands if the slider is in the right orientation, and if not, then it will flip them. So what I said, pick, place, and flip. And now you can see they're being put into this form. And now given to another robot that then takes them, flips them, given to another robot that then takes them and puts them into the machine. Obviously, this is not at full speed, but we were able, I think, to automate this for about $25,000. So almost more than half the cost, way quicker. And that is why this also made sense to automate, because you can imagine these are small, metal sliders with a little bit of plastic around. They don't cost that much, and we don't sell them for much. So getting a $70,000 system for each of these injection molding machines just wouldn't really pay off. So that's why we were stuck with humans. And that is not a fun job, to put these things into the machine all day, every day. That is not a fun job. So that's one of the examples of low-cost automation, how we use it in our facility. But we can also apply it to all kinds of other systems. Cool. So that's what we define as low-cost automation. As our sales team was, going out and offering people our robots that we make, the gantry solutions, the Delta, the robot arms, we did, though, find that most customers were definitely still overwhelmed with working just with the robot, because they still have to find, hey, how do I mount this robot? What kind of hand end effector gripper has to be at the end of the robot? And how do they all work together? Just an example, you have the robot, and then you have the gripper, then you have to figure out how to mount the gripper to the robot. You have to understand, does this gripper even communicate with the robot? How does this work? I don't know. So we got to a position where we were actually recommending most of the systems to people, grippers, cameras, conveyor belts, all this kinds of stuff that you look at industrial automation. So that's why we came up with RBTX, a marketplace, where we would sell, but also consult on other companies' components and robots. So we not only sell our robots on there, we also sell other people's robots that might fit different applications than ours. Because obviously it's really hard to make a robot that can do anything. You will never be price competitive there. And I think this is kind of where we dive into what I mean with open source or semi-open source. So the idea of this marketplace is that instead of building an automation closed operating system, we want to build a semi-open source marketplace. This is the same for our robot, but also for us. You see many of our competitors out there that try to build this nice software platform for robotics and automation. And they have all these components that can integrate it, and it's a neat little software, and very expensive too, but because it requires a lot of development. But we really see that it's really, really hard to build an operating system for industrial automation or for your factory. So what we try to do is we try to keep it open source in the sense that you can add any components to it that you want. And all of our robots you can buy with control or without control. So let's say you want to put your own controller on our robot, that is totally possible. So this, in general, this is the platform, and I might as well switch to the newest platform now. Yeah. So the platform kind of consists of products that we offer. So these are like our robots here, but you can also see universal robots. That's maybe a robot brand that you've heard of, Epson robots, and all kinds of stuff. One thing that we do is we're super price transparent. So all the prices are listed on our platform. For most of these products, you won't really find them anywhere else, or it's not the list price. So that's something that people really appreciate about the platform. You can see all kinds of grippers, yeah, pneumatics, but also other accessories that range from, robot covers over 7th axes, cubes, framing, all this kinds of stuff. And then secondly, we go into the applications. What we do is we list all the applications that we're allowed to share, but successfully implemented. We list them on this platform so people can browse around and kind of understand how we solve the problem. Let's go in here. This is an application that we built for trade shows. So not a real application, but still a really good one to show, where somebody that is new to automation could go in here and kind of like see how we solve the problem. So this is our Rebel, our robot arm. It's our low cost robot arm for $7,000. Every one of these solutions have a price with them and a video, so you know exactly how much it costs. You know exactly how it works, because the video typically shows you really well. So in this example, they have some circuit boards that are rotating, and then the robot is taking pictures of them by having a camera at the end of the robot arm. You can learn more about this in the text, and then you have all the components that were used in this application. So for somebody that is challenged with their boss came into the office in the morning and they're like, you know what, Ben, I really want you to now automate this process. And Ben is like, I don't know how am I even going to start? They can come on here, figure out how we did it, and then kind of, do it themselves, or reach out to us and we can do it for them. Another interesting fact is you can, find all the information on all the components, and you can book a free call with us where we can just help them. But the idea really is that, people can choose these components, put them together, and let's say I'd add them to the cart. The platform is designed to improve or like simplify the process and take away work from the consumer. So basically, you just chose the camera and the robot, and it will actually include the mounting kit for the camera. This means that typically, if you go to a company and you order this camera, they will send you the camera, and then you'll be like, well, I do need cables, right, to plug them in. And they're like, well, you didn't say that. So every time you buy something, you need to figure out, you have to go through their catalog. They probably have thousands of cables. And then they're like, well, do you want it in 1 meter, 1.5 meters, 2 meters, 3.5 meters, 5 meters, 10 meters? Do you want to shield it? Do you want an ESC? I don't know. So basically what we do is we include this automatically, so that it's easy for you and you don't have to worry about it. That is the idea of like how to simplify kind of working it together. Also, on the other hand, what the system does is it shows you which components don't work. So you can see all of these grippers that would work with this combination of, camera and robot. But then if you scroll down, you also see all the grippers that don't work. So some of our partners, but also just any really industrial automation company that provides components, they have a lot of variances. They pride themselves. You go onto the website of a gripper company and you're like, I think I need that gripper. That is only the beginning of your search. Because if you go in there, then you see they have 2,000 variants of that same gripper with all kinds of different add-ons and everything else. So what we do is we just pick one, and then that might not be the perfect gripper for you out of the 2,000s, but we know that they work. So that's the idea of the platform. Yeah, let's say we add that gripper. We add that to the robot. And you should see we didn't only add the cobot pump, we also added the mounting plate and the screws. And yeah, the cable is already included in that gripper. So ideally, if you get this package, you should be able to screw it together. We do have a big wiki page that explains kind of like how to do this. And this is kind of our approach to making sure that somebody that's interested and maybe has some engineering background can build their own automation systems. Cool. On the other hand, we have over 400 solutions. And then if customers really, if we don't think, we recommend them, if they really don't have the capability to automate, then we also have a partner network that is not only components. So these are components, you know, Schmalz is a gripper company, but we also have industrial engineering companies that basically can design the systems for you and build them for you as well. All under the idea of low cost. So what is the best component for the best value? What is the best service for the best value? So that's the idea of doing this. Now, that is kind of why I'm really passionate about open source, is because I see many, many companies out there that build productized solutions that are fully enclosed, kind of like iOS. So I always describe us as the Android of industrial automation, where we're trying to build a platform. We're trying to make it easy to integrate and kind of like something to build off of. But I want to keep it open so that people can add stuff, they can take stuff out. They can choose to, you know, run the whole thing on ROS if they want. They can use our controller. So that is the important stuff, part, where we don't want to become the iOS, because for automation, in my opinion, that will never work unless you really specialize in one specific use case. Let's say I really want to put caps, the cap of the pen onto the pen. Fine. If I just make a solution for that, I might be able to get away with a closed kind of like automation system. Cool. That is kind of like the platform idea of RBTX, where you can get components, find solutions, do that. I think in the next step, I wanted to show the actual software that we wrote, and feel free to be critical. Be aware that we're a plastics manufacturer that started building software, but it is kind of cool, and I'm excited to show you. So I guess started not with this platform, but they started with the whole robot idea. How can we make systems that are affordable? So we tend to be about half of the cost of other competitive solutions. In the robot arm space, we're almost a third to a fourth of the cost of other robot arms. You can see here, all of our robots, funny enough, their controller is based on a Raspberry Pi that is a little bit modified. But the nice thing about it is that they can all be controlled with the same software interface. So you can select your project here, and this software is free. You can download it online and just play around yourself if you really want to. Actually, it's pretty cool. You can program all kinds of stuff, and it has a bunch of APIs and interfaces as well. So you can see we have different kind of Delta robot. We have 3 axes. They have like, you know, three dimension kind of, and then the 2 axes kind of more of a plane that goes up and down that you control with this. Gantries. Gantries are just linear actuators that you can kind of make all kinds of weird systems with it. You can see here, this is like 2 Z axes that are on the other side. Then you have lead screws, you have really, really long ones, and so on. Scour robots, they're also pretty quick. It's a different kinematic. And then the robot arms. These are our robot arms here. All kinds of degrees of freedom, 4 degrees of freedom, 6 degrees of freedom, 5 degrees of freedom, but also each individual axis. So let's say you don't really want to buy our robot, you can just buy each of the axes and build your own. So you can just program each axis individually. These are our RoboLinks. This is the predecessor to the Rebel. They're industrial robot and not a cobot. And then, you know, kind of like the same with these. If you just want to buy these actuators and you make your own secret project out of them, you can just do that. with this. So let's do the robot arm because I think it's the coolest. It's really easy to program in here. You basically just go into the edit function, and then you can open in another window. You can see this, right? Cool. Yeah, you just write line by line, 7 digital inputs and outputs. You can do joint commands where you just control one joint and then move it to the position, or you do linear commands where basically you just tell the robot from the end effector, end of the robot, go from this point to this point. So a little bit more straightforward, all kinds of functions, but in the end, pretty easy to edit. You can add motion commands, you can add logic, you can write separate logic programs in the back. Pretty cool. But then I think the power of this is that it looks like Excel or PowerPoint or Word. So anyone that kind of like opens this up is kind of like familiar with it in the first place. Other robot companies, they have like their own fancy interface. It's all kind of like optimized. But in the end of the day, we want that somebody that works in a factory can program this. And we don't want them to spend 20 hours on learning and watching YouTube videos. We just want this to feel natural. So there's multiple ways that you can, and I stop this here, that you can program this. Once you can just drag this and program this way, where basically it records the position and you can just make a new point out of any position. You can teach it in. You can also, control each joint down here. You can switch from joint profiles to base profiles. Now it's just X, Y, Z. And you can choose the speed up here. So super, super easy. I don't think I've ever gotten a training on it, and I'm super comfortable to explain it to anyone. And yeah, this is also a digital twin. So if you connect it to the robot, you will see the position of the actual robot. You can control it with the gaming controller, which is quite fun. We have camera integrations, and this is kind of the system that we built on. We built on APIs that it's easy to program, but we also built on adding more functions like vision and all this kinds of stuff to the software to make it easy. This is all to say that you can buy this robot as the robot plug-and-play version with the software that is free, or we rip out the controller for you and you can just control it with your own software. That's what we call the open source robots. So all of our robots, you can also just buy the hardware and then do your own do-it-yourself robots, which there's many of them, and there's a bunch of cool YouTube videos on that as well. I think that was basically what I wanted to show you. I hope it was interesting, and I hope you have a lot of questions, but that's what we're trying to do, trying to disrupt the market by being lower cost and easier to deal with, and hopefully helping a lot of companies along the way.
Yeah, and that's super cool. Thanks for sharing.
Yeah.
Maybe I'll start us with a question. So, like I don't know hardware at all, but in software, we spend most of our time debugging, I feel like. I think I spend more time debugging than actually writing new code, especially when I have to work with existing code, from open source projects or whatever. I would imagine that, correct me if I'm wrong, but probably a lot of the cost in a robot would be related to when something goes wrong, like not only how expensive it is to fix it, but also how much money you lose waiting until it is fixed, right, on the factory floor. So is that something you guys think about with robots, like trying to design them to be, design systems that are not just kind of cheap to build, but also cheap to fix, or have like low downtime, that sort of analysis? And how does that play into things?
Yeah, that's awesome. A really good question. One of the, basically at the moment, the way that a company goes about building an automation system is they go to an integrator. That's what they're called. And that company basically builds you a machine that does it. The main problem with this model is that those integrators, they're really busy with building new machines. They don't have time, or nor do they want to troubleshoot machines that are broken from them. So there's many, many companies that have started automation and now have a system in their warehouse or somewhere that just doesn't run anymore. And so they've kind of given up on working with these together. Our system is a little bit different, where with the platform as RBTX, we want to offer service plans, or we do offer service plans, where once a year we come by, we do a visual checkup in person of the system and make sure that you can deal with it. But also on the other hand, all of our systems have log files. So you can just go on here, collect the log files of the robot. Now I'm not connected to a robot, so it won't collect them. Yep, it just gave me the error. But you can then just contact our support team and we will help you out. This is a big selling point for us, that we will support the robots. And most of the time we're able to fix it remotely through those log files of the robot. You can see, oh my God, this motor has a temperature error or something like that. And sometimes you're even able to do this here. So for example, here you can see I had a connection error because obviously I'm not connected to a robot. So that's kind of the path there.
What's the weirdest industry you've supported working on? I mean, I know, just for context, before you were doing this, you were making like robots that made micro pipettes, right? Which is also pretty peculiar. Not it's interesting and somebody has to do it, but not what people maybe think of immediately when they think of robots, right? So like I'm just curious, like what's like the strangest industry you've helped with that you can talk about?
There's well, there is some robots that are being used in the adult entertainment industry, but I think that is probably the weirdest. But then there's also robots like there are companies that try to mimic psychedelic experiences, and they use automated systems for that. So that was very weird, that I never thought about. And then in general, there's just a lot of like something I would have never imagined before is quality control or vision, because those cameras that are being used are very expensive. They're upwards of $30,000 sometimes. So if you can get a robot arm that can reposition the camera, that saves you a lot of cameras for different angles, right? So that was something I never expected, that if you have a $7,000 robot arm, you can reposition cameras and then save a lot of money there. Other than that, nothing too surprising, I think.
That's what you were doing for Certina, right? I saw like the picture of the Certina watches.
Yeah. So we were moving around to do take pictures, and then that picture gets analyzed on the back end. Okay. So most of the time the robot arm is there to take the picture. But yeah.
Great talk. Maybe I could chime in here with a question. So Max kind of kicked us off with more of a software-oriented one about debugging. I used to do competitive robotics, and one of the things that was nice there is we had a firm end date, right? So in these industrial environments, there's not that, and so I feel like there would be a long maintenance tail for these automated systems. So when you guys are developing your cost models, are you taking that into consideration? And like, is that something that a customer of yours is aware of, right? Maybe I have a choice between two arms. One's more expensive, but is less prone to breakages, or parts are more readily available and stuff is more maintainable. Is that something you could speak to at all?
Yeah. So I mentioned it earlier. So basically our company's base technology, something that they started 80 years ago, was engineered plastics, so like performance polymers. And one thing that they do with those plastics that we use is they infuse lubrication into the actual plastic material. So when they mold it, the lubrication is being molded into the material. And so if you talk about wear and maintenance, it's usually about motion or sliding parts like gears and stuff like that have to be lubricated. If they aren't lubricated the correct way, too much or too little or not at all, then those components break and then you have to replace the parts. Typically for most robots, if you do everything well, it's fine. But going back to the original points, so basically what we developed is our plastic robot doesn't use lubrication. You don't have to maintain them. It's basically maintenance free. That's what we call it. our gantries, they have, instead of ball bearings, I don't know if this says something to you, but ball bearings, basically they're little balls that, slide around and they roll instead of sliding. They have to be lubricated and they break. For us, we have sliding elements. They're kind of like plain bearings. So they kind of touch on the surface of the rod and then they slide. And then over time, they also, degrade at some point. But what you can do is you can just take the carriage off and take that plain bearing and push a new one in. So for about $2 to $3, you can just like exchange all of those things. Same for the robot arm. The robot arm comes with 3D printed gears. And if one of those breaks, God forbid, you can just get another one for $2 and put them back in. So that's kind of the idea, where we call our robots maintenance free. And we also test them to the extent where we know, hey, if you use this robot, like with this use case, you should think about every 2 years to kind of change that gear or to change that plain bearing. But this is all something that we bake into it, and we try to communicate that when you get the robot. And I think that's the strategy to lower the maintenance cost as well. And if you send us the log files, we know exactly how many cycles your robot did. And therefore we can say, hey, you should start thinking about this. So part of our support package is that you can send us the log files once a month. And we have somebody look over them to make sure that everything looks to be all right.
Awesome answer. Thank you.
So funny story about this, Rez.
Oh, sorry.
Oh, sorry. Go ahead.
I just had a quick question. So very interesting. I was curious about the tool or the part of the website, I guess, that tells you about like pieces that work together. And you mentioned that there's loads of different options, like different types of pieces, parts you can put together. So when you say like that that these two components work well together, is it because your company has actually built a system that uses those two parts together? Or is there some like automated, like, is this automated, like that the matching of components that are compatible? Yeah. Like, how is that done? Like, is it just through experience? And kind of related to that question, I wanted to know, like, what if a customer comes and they want to use products A and B together, and that products A and B together work well, and A and C together, and that A and C work together well, but you've never tried A, B, C together all at once. So is there any possibility that by like using all these three components together, then all of a sudden they're not compatible? Like, is there those situations that ever arise? I guess that's also something I'm interested in.
Yeah. So we try to kind of keep the optionality fairly low. So there's for the matrix themselves, we try to not add components that have, if you look at an application map and every component is a bubble on that application map, we try to not have these bubbles overlapping. So thereby we reduce the amount of options. And that's kind of the way that we achieved a fairly low component count on our website. I think we're about 350 different components that we then have to, make sure that they're compatible, or make sure that we know that they're not compatible. Right now, all of this is done by hand.
Okay.
And most of these components have been tested as well. But it's fairly easy to say. There's just standard industry communication protocols. It's like you can I/O signals, for example, that's just a 24-volt signal. If the gripper can be actuated with that, it's very, very easy to assume that the gripper would work. Now, for our robot, you get the power for the gripper from the robot. You just have to make sure the amperage and the voltage is good. So that's the way that works. So it's a big Excel spreadsheet, big file that whenever we add something, we add a bunch of different, we have to think about all the different components. And we tend to say, okay, this doesn't work. So we tend to err on the side of caution than on the risky thing. to your second part, there might be situations where if you, let's say, you can put multiple grippers on the same robot. Right? So you could actually have kind of like an adapter plate that puts two grippers on the same robot, and then the robot just uses that and then uses the other one for a different task. And so I assume there would be options where somebody could buy too many grippers, and then to, you know, carry the amperage of those grippers at the same time would be too much for the robot, and then it fails. And I don't think that's baked into the algorithm, or like into that Excel spreadsheet.
So yeah, so you could pick components that individually are compatible, but they're, since it's kind of still like a spreadsheet. So like, I guess what's interesting is like, I mean, a lot of effort has to go into making sure that you manage or curate like your products, like you said, where you kind of have one, you pick out a good product that does task like X, and you try not to add too many more products that also satisfy X, because then you have like more overhead, because then every time you add a new product to your spreadsheet, someone has to go and check, like, for all of the other products we have, how does it play with those? So that's a pretty interesting, and I guess that's the interesting part for me, is how do you, like, as you grow or you want to support more type of tasks, like it becomes harder every time you'd like to add a new product. So that's, yeah, so that's interesting.
Yeah, for sure it is. It's going to be harder. But we also, I mean, the one good thing is that any given categories, only we look at the compatibility to its add-ons. So we don't really assume that our robot is compatible with another robot of itself, right? We wouldn't say, okay, our robot is compatible with its sibling, basically. So, and we would also not say our robot is compatible to a universal robot. What we are concerned with is that the robot works with the gripper, or that the robot works, you know, even with a camera system that is integratable or not. That's
yeah, so it's more like not everything is related with compatibility, just like a given robot with accessories potentially.
Yeah, the important thing is if the main control system of the system can communicate with all controllable components of the system. So let's say if I buy a industrial lamp that I just plug into an outlet and then it's on, so that it doesn't, I don't have to check compatibility unless I kind of want to wire that into the robot, which I don't really want to. But what I care about is that I can control the conveyor that moves components, and that I can control safety, so that, you know, safety interlocks or safety scanners or so on work with the system. Which, you know, with safety, you kind of outsource that to a master controller anyways. So I think what we're mainly concerned about is actually the gripper compatibility. So that the robot can, that in the software here, I can control the gripper of the robot. So if I go here,
like in the software, if you try to like add a gripper to the robot and they, like, at least, you know, it'll tell you here that they're not compatible, is what you're saying. Yeah, that makes sense. Yeah,
so that you don't buy something that will never work together.
Yeah, that makes sense.
Typically the way that the industry works is usually you buy individual components, and then you buy a master computer, a PLC, programmable logic controller, that then controls everything individually, and then you program that. But here we try to kind of base it on the robot base. But sometimes you just need that. There's no way to go around it at that point.
Yeah, thank you. Interesting.
Yeah, no, that's a good question. How I'd like to make sure that if you,
it's like it's the question about the inventory, I guess. The inventory management is like that whole topic.
Like A, B, works, AC works, but ABC doesn't. Yeah.
You were showing some code before, and it has like explicit coordinates in it. Is that the way that programmers in this space are accustomed to working, or are there like higher level languages that will use some sort of stat solving or something to figure out what the coordinates would be based off abstract instructions, like pick this thing up here, put it down over there, and then it like derives, the arc it goes through in order to do that?
You mean the position or the
Yeah.
way to go there?
Yeah, exactly. Like, you could say, move the arm to this position, move it to this position, go down, pick up, or you could just be like, pick that thing up, right? But if you had a language that just said, pick that thing up, put it over here, then the robot would have to figure out how it moves through space in order to accomplish that goal, which would mean that basically your compiler has to do all the math to figure out like an arc it can go through without hitting anything. And I'm wondering, is that something that people do in robotics? Like, are people accustomed to having a higher level language like that, or are people pretty accustomed to explicitly writing down the coordinates that they want to move through in order to accomplish some task?
Depends on if you're space constrained, then you kind of make sure that the robot moves the right way. Otherwise, most of these GUIs have inverse kinematics that are being used, where basically I haven't looked at that specifically, but let's say I want to go down in Z. The robot will figure out how it does that.
Got it. Okay.
And there's a lot of different ways, right? It could have disjoined and then go out on the side and kind of do that, or the other way. So that's fairly common, where you use inverse kinematics and then do that. Sometimes what people do is they do through points. So you say, hey, go to this position up here in the shelf to do something, but I want you to pass through this point to make sure that it doesn't like crash into the shelf from the bottom or something like that.
Right. Okay. Do you get wacky stuff with the inverse kinematics? Like I've seen, for example, if you're not using quaternions, if you use like Euler angles, you can get these screwy arcs that from a robot. Does it ever come up with something that's really bizarre and you're just like not really sure why I did that?
Yeah, so you can get basically if two axes are aligned with each other, and then you tell it to move somewhere, then it doesn't know which axis to move, because you could go this way or that way. And that's a very common error because it's all a matrix, and I haven't looked at the math, but basically what I've been told is that there's a 0 somewhere and you try to divide by 0. Not sure why. But
that makes sense.
Called the I'm trying to replicate it. It's not that easy. Let's see. Basically, let's do this to 0. I think if we put this to 0.
Oh, it won't let you. I think it'll go to 0.1 or minus 0.1. Probably for that reason. Yeah.
Oh, there we go.
Okay.
Then if I move from here, come on, we can do this. So, and now I go into now it can't move.
Right. Okay.
Center
it's sort of like a gimbal lock or something. Yeah,
because of the math that's in there, which is that's always. So that's when you program a robot, you always have to make sure all the axes are kind of bent.
Yeah.
If it's straight up, then you kind of you have some issues.
Yeah, it seems like an interesting code synthesis problem. You could have like a nice little formal methods paper or PL paper where you come up with a high level language that can detect when it's in an error state like this, and then it has like some sort of alternative mathematical routine to figure out the solution, right? So
it's really important that, let's say you're looking at an application, maybe you have a camera system that tells the robot to go somewhere, and then by accident it goes through that point, then that's a big issue, right?
Right.
So you need some form of error protection there.
Yeah, that's interesting.
Error handling. Yeah.
How much time do you personally... Oh, go ahead, Chris.
Yeah, I had a question relative to your emphasis on cost. I understand you want to reduce it, but help me to understand when people are implementing these customizations, these robotics, is the life of the solution months, years, or decades?
So our solutions are typically 10 years. That's the goal.
Okay.
But it really depends, right? So if you have it depends on the duty cycle on the motors of the system. So if your motor runs at 30% duty cycle, so 30% of what the motor can do, then the system will last really long. But if you have an application that you need a lot of acceleration, lots of high loads, and your system is kind of designed at like 80 or 90% of the duty cycle, then you should be expecting it not to last as long. Okay. And then there's also the industrial, the settings where a robot moves 24/7, or the cycle. Typically, we assume that a robot arm picks something, places it down, has a couple seconds, and then does the same over again. But if the robot is running continuously, that also plays into the role. So I guess to answer your question, it always depends what you need. And that is one of the reasons that we do have other robots on the platform as well. So for example, some of these Epson robots, they were designed for mechanical watch assembly, which is something that runs kind of like 24/7 and is super precise and a really long time. Whereas I would say our robots are meant to be more in the light duty realm, where maybe you have the machine running for a couple hours a day, and don't accrue as many cycles.
Okay. And when it comes down to these robotic solutions, if you have to swap out, say, the arm that you have for another arm that's on the marketplace, is the programming basically the same, or are you starting back at zero and programming it all the way on through with that interface you were showing? Or do you end up having, if you swap out this arm for something from, say, Epson, having to come up with yet another interface in order to do the programming? What's the reality there?
We're designing a product right now. We call it the Any app. Let me see. We have it here. It's in software. And the Any app is basically the same interface, but for other robot arms. It's a product that is fairly new. And I don't think it is fully released yet. But I think at the beginning of next year, we will be able to kind of program all kinds of other robots, even the Epson robots from the software, which is going to be exciting. So I guess that's part of the mission, to make it easier to program robots. And if you have to learn how to program a Fanuc, a universal robot, an Epson, and an IGUS robot, that's kind of an education itself, I guess.
A difficulty. Yeah. What I'm thinking about is back in, say, the mid 80s, IBM started to refocus their software development folks. They basically supported COBOL and C and Fortran, a number of different languages. What they found is that their customers basically stuck to these languages, and once they had invested heavily, they basically painted themselves into a corner. Either they had to get people with that particular language proficiency, or they were SOL. What they ended up doing is finding a way to write their programming languages in such a way that you could write something in C that worked with or interfaced to an application written in COBOL or Fortran, and basically busted that nut so that you could use any of the programming languages anywheres, and it made no difference at all. It feels to me very much like what you're talking about with this Any app
Yeah.
is the possibility of creating something universal. Think of it as open source, think of it as a standard API interface for all these different components so that you could have a common gateway to the components that the software could speak to. Is that fair to say?
Yeah. Yeah. And it starts with the robots and then it goes into the add-ons like the grippers. You know, if you figure out how to send the signal to the gripper directly, you can integrate that into the software. Same for the camera. And I think you can see that already in the industry that companies typically, if a new like if a car manufacturer builds a new car factory, they choose one robot brand on purpose. They don't go around and say, hey, this robot from this company and this robot from this company, because that makes sense. It's because if they have to train their people on all kinds of different robots, it's going to be super, super difficult. And being an expert in one is very valuable. So they just say, hey, I have this plant, I need 3,000 robot arms, and then they just buy it from one company, even though it might not be the best product for the specific application.
Yeah, but that still speaks to your assertion that if you have a robot arm and it gets to good enough to pick up, say, a hockey puck off of a conveyor belt, that's a radically different set of tolerances than going to the folks that made the Swiss watches.
Yeah. And so I guess what this Any app or like any other service that is trying to do this provides is that you can just choose the best component with the best value for the specific application.
It's an interesting
super cool.
application you're trying to work with. This is quite a challenge, and this has got to be a lot of fun.
I love it. Every day there come different applications, different problems, and it's a lot of brainstorming, but it's really cool. And you know, one of the most satisfying things is that we can reliably deliver fully automated systems for under $100,000, which is something that there's very little out in the market. And for most of the competitors, even they don't compete in this space because they don't make money. And due to the fact that we can kind of leverage this platform, we can actually be very cost efficient and help people that wouldn't really been able to automate before because they can't do it themselves. So
from Swiss watches to adult entertainment.
Exactly.
Sick. Cool. That's probably a good place to sign off. So yeah, and thank you so much for talking to us. It's really fun. If people want to reach out to you, can they email you? What's the best way for them to get in contact?
Yeah, email, LinkedIn. I can put it in the chat. Does that work?
Sure. I'll share. Well, why don't you put it in the Slack? Because I think you're already in the Slack, right? Or you can send your email to me and I'll put it in the Slack either way.
Yeah.
But
ironman.net. But yeah, you can also find me on LinkedIn, and also you can just go on RBTX and then sign up for one of those calls, and someone from the team will show you the robotics lab. So those calls, you'll land directly for a free 30-minute call in the robotics lab in Rhode Island, where we have all our robots and other robots, and then we can just show you some of the stuff that we have there.
Very cool.
Free to just sign up. No need to,
to buy a $100,000 robot.
No need to buy anything. It's all free.
Sounds good. Thank you, Jan. It was a lot of fun.
Thank you.
Thank you.
Bye.